All right, questions? I'm only like 2 seconds early. Nothing? You can do all the work? All right, so if we kind of summarize what we're supposed to do at this point, we're supposed to be able to go through particular problems and we could take something like we've already say B denotes the sky is blue. So we should be able to do variables, and so we've done propositions. From propositions, we're able to go from tables, and then we also have the idea of compound propositions. With the idea of the operations and orders of operations. And then also from our compound propositions, we last did on the idea of 1.3 was the idea of the sameness, which is, again, logically equivalent. So far we should be able to take anything that looks like sentence, write it as a label. If I just have a label and no sentence, we should be able to create tables. We should stuff them all together with compound propositions and operations and grouping symbols and the truth tables for them. We should be able to go back and forth between the language and the symbols and the language. Say it however we want. We should be able to talk about the things like when are they the same under logical equivalency and under compound propositions. And the way to do this is we've learned you should be able to do it 3 ways. You should be able to use a table, which is the idea is the biconditional of tautology. 2, you want to either show true in exact same conditions. Conditions really means that as a table, that's a row, right? It's for these particular truth values of the simple propositions, P, Q, and R, whatever you're dealing with, that for any particular one of those, it'll end up being true in the exact same conditions. Or if you wanted to, you could simply show false in exact same conditions. Why do I only need to do one of these? You can do both if you want, doesn't really help you. But why do we only do one of these? It's because, well, there's only true and false. You handle true and false is because false is everything else. So we only have to pick one. When you would choose one or the other for these exact same conditions, you would pick the one that is most rare. You can do either true or false. The example of this under argument was the idea that, for example, yes, P implies Q. What is the disjunctive form of implication? If I would write an implication using the word or, what would I use? Not P or Q. So if I ever say the disjunctive form of implication, that's what I'm talking about. Okay? A truth table would be biconditional as a tautology. An argument would be, well, we would look at this and say, well, for implication, what's the most rare event? False, because it goes what? True implies true is true. True implies false is false. False implies anything is true. So false implies true is true, and false implies false is true, right? So I really don't, false would be the thing that doesn't occur the most often. And so that would be the one that would make the most sense. We would ask when false, right? You'd go through this and say, when false. Well, for the left side, it is P is true, Q is false. What about the right side? That's a little more work, right? It would be the same, but why? What's the only possibility for a or to be false? Right, for the right side, we would have to have not P is false and Q is false, but not P is false really says what? P is true. And so, same conditions. So, exact same conditions. So that means they're logically equivalent. Yes?
Does that mean, is that method always correct?
Yeah,
Or
yeah.
it's not going to miss out on stuff?
Nothing.
Like really?
Yep, nothing. It will miss out on nothing because there's only true and false. Right? There's only true and false. So it is only going to be false under these under this one condition, right? And then I look at the other side. It will only be false under this one condition, but those are the same conditions. So we're done. And ask, well, what about true? Well, true's everything else. True's not false, right? So not those conditions is not false. So we're done.
But in this case, there's like only one condition. What happens if there's multiple conditions?
Same thing.
Multiple falses and multiple trues?
Yeah, same thing. You just have to show that those conditions. Like, if you would get something that would have, what would be sometimes true? Well, we could split it. Who's half? Exclusive or, which is not the biconditional, right? We would say, for another example, what if P exclusive or Q is logically the same as not P if and only if Q, right? Now it's 50-50, right? Exclusive or is half time true, half time false, so it really doesn't matter which one you pick. So what do you want to pick? When true or when false? Which one?
True.
All right, let's do a when true. Okay, for the left. When is the left side true? 2 times, right? When's the left-hand side true?
P is true and Q is false.
P true. Forgot that. P is true. Q is false. And P is false. Q is true, right? Those are the only 2 conditions. All right, what about the right? Which is that whole, it is not P if and only if Q. When is that true? This is true when what? When P if and only if Q is false, right? A not something is true only if the something is false. When is the biconditional false? What does the biconditional do? It checks for sameness. And so this is false when they are of opposite values. But when are opposite values? 1, P is true, Q is false is one condition, or 2, P is false, Q is true. Same? We're done. Those 2 conditions, one occurs in only 2 conditions, the second only occurs in 2 conditions. Those conditions are exactly identical, so therefore they have to be logically equivalent. So, exact same conditions. And again, people are like, well, what about when false? It's like, not it, right? Not those conditions. That's the only possibility. It's either true or false. So if you not it, we would have the exact opposite. Why do we usually focus on rarity? So we have as few of conditions as possible. So if I did the original problem and asked, like the implication one, and I asked, if I asked when true, I would have 3 conditions, and the other one would have 3 conditions, and we'd have to show that those 3 conditions are that way. Obviously, this gets more fun when we have things like multiple rows, right? We have 16 possibilities, and then 6 of the times it's false, and 10 of the times it's true. You'd focus on the false, but you're still going to get 6 conditions. Can you see why sometimes an argumentative process, when it gets complicated, is a little bit hard to work with? It's not bad if it's rare. It's only going to be false in this condition. Oh, good. There's one thing to look at, so let's look at it. All right, and then again, the third way of doing this is the idea of just simply use old logical equivalencies. And that would be, like, again, that implication. You know, P implies Q. That's logically the same as, actually, let's do this one. Not P implies Q is logically the same thing as not P or Q. What did that use? That used the disjunctive form of implication. But that's logically the same thing as not P and not Q. What did I just use? Distribution of negation is also called De Morgan's. And then what's double negation? What's not P? P and not Q. Right? And so we're done. And so it is true that not an implication is the same thing as having the hypothesis and not having the conclusion. This is actually an important one to know. We'll use this a lot later. One of the reasons why is sometimes we're interested in showing that P implies Q is always true for certain P's and Q's, right? But that's really, really hard for us to do. Well, then you could back off and say, well, I wonder what not P implies Q is. Well, it's P and not Q. Well, if I want to show P implies Q is true, but it's too hard, it'd be the same thing as showing that not P implies Q is what? False. And that's a proof. That's a technique called proof. We'll eventually do this, proof by contradiction. Showing something's always false, its opposite must have been true. So those are the three techniques that we need to be able to do. And it really just simply gets down to, like on this third one, it's like, propositional algebra. These symbols become these symbols, become these symbols, become these symbols, all according to this particular law. But you should be able to do all three techniques. All right. If we go back a little bit and we look at, say, B denotes the sky is blue. And let's study propositions for a second. In other words, before it was just they're a proposition. They're either true or false, but not both. We just have it. But there's something that we notice about all propositions. The only possibility to be a proposition is to declare something about something. Right? If I would look at this, we have two things that are occurring here. We have skies and we have this is blue. The sky itself is acting as an object of interest. And is blue is actually a property, the object of interest. Basically, it's who you're talking about. Has or does not have, right? And I can play around with this a little bit. I could pick different properties, like the sky is green, the sky is purple. I could test for different things. I could throw in different things. The sky is blue. Mark is blue. Right? The wall is blue. The sad little puppy on the side of the road is blue. Right? When we go through these particular things, we have every declarative sentence has an object of interest, the thing you're talking about, and the property that it's supposed to have that you're declaring. It has this, and if it doesn't, the answer is false. If it does, the answer is true. And since every one of these have this feature, we can kind of ask ourselves that we're going to give the property test its own name. The property of the object, we are simply going to denote, we'll simply call this a predicate. So a predicate is the thing that the feature it's supposed to have. So if I said, my name is Mark, what's the predicate?
So your name is Mark.
Mark, right, the name of Mark, right? The sky is blue, what's the predicate? Being blue, right? This person is taller than 6 feet. Being taller than 6 feet. X is greater than 5. greater than 5, right? And so this could be a mathematical thing, this could be a emotion, this person's happy, this person's sad, this person's blue. Well, that might be an emotion, it might be a color, right? So the predicates are the thing that we're testing, and then we have the objects themselves. And then what I could do is I can take a proposition like this and turn it into what's called a propositional function. Right. A function is a rule that takes things out of a domain. So over here is a domain. Here's my rule. Let's simply call it, for this one, let's call it B instead of, well, let's use F for function for now. Over here is, what's the thing on the right? Things in the domain get mapped to things in the enclosed codomain. The range is the values that you actually get to. For example, the codomain is chairs, are desks in this room. So what's my domain? Students. There was a rule, I don't know what it was, you guys made it up yourself, to sit where you're sitting, right? So there was a function that happened here, and you all came in and sat down. What was the codomain? The places that you could be at, right? What's the range? The places you're actually at. All these empty desks are not part of the range, but they are part of the codomain. So that's the difference between the two. And what happens under propositional functions is they take anything in the domain and simply map it to a true or a false. And what this would look like, and over here in the domain, is also called the universe of discourse. Really, it's the stuff you're talking about. And so an example would be, let's say we did, and normally we would, when we do functions, we move into capital letters. And so I would say, for example, B of x denotes x is blue. This is not a proposition. If I say x is blue, it's true or false, but no. I don't know if it's true or false. I have no idea what the truth value is, literally because it cannot return a truth value as is, because what is x? X isn't actually an x, right? What are variables of propositional functions? The variables of propositional functions, if I would have instead of x, I would rather have written B of something is that thing being blue, right? That's what the variable, the x really represents, fill me with something. Put something here. So it really is blank is blue. That's not a proposition. But if I put things in it, Mark is blue. It's either true or false. The sky is blue. It's either true or false. Right? It then is capable of being evaluated as a proposition, being true or false. So notation-wise, we usually use x because it's a bad habit. This is also where we would pick things like labels would be appropriate. Normally when you do the text and you're going to do things, you would pick a capital letter according to the predicate. So if in the homework it says, talking about being a comedian, you ought to use C. Talks about being funny, you ought to use an F. Right? Or better yet, write the word comedian. Comedian X is a comedian, comedian of X. Funny, funny of X. Just give it a longer name if you want. Makes it easier to read. All right. All of these, we leave the predicate gets the label of the function itself. Again, there's lots of different examples that we could do on this. Is f of, say, p denotes p is funny. We could do h of d denotes d is funny. Sorry, funny. Happy is what I was thinking about. Happy. Right? Again, is that P actually P? No. It's a blank spot. I have to put a label of some sort. So one of the reasons why when you do, if you're first learning function notation, you usually don't want to pick things like X, Y, and Z like the book does. It's usually better to pick an open symbol like O, something that can fill in the gap and it's also when I first teach it for people that have never seen functions before, I tend to always reuse squares and triangles and things that I can write stuff in. It's really useful for calculus, right? When we say things like, what is a derivative? It's f of x plus h minus f of x all over h. And then you'd ask, well, what's f of x? It's really useful when you do that sort of notation. If you would say f of anything is that thing cubed plus that thing, right? And then when a person says, what's x plus h? X plus h, x plus h, x plus h, right? Whatever goes in is where it goes. So that's a good way of learning functions for the first time. And so if you teach anybody else like calculus, that's a great notation to use because it gets, everybody else has a really bad habit of doing this. You know, x plus h, and they do this, x, h. And you go, darn, no. That's not what we're talking about, right? All right. So we've got these guys being funny, happy, however you work with it. One of the other problems that we have is what's the domain of propositional functions, right? This is the set of stuff you are talking about, right? There's a reason why we say that the domain of a propositional function is also called the universe of discourse. What in the world are you talking about is the narrowing down of it. Now, if it is not given to you, these are either one, if they're just simply given, right? I could say L of xy denotes x loves to eat y. Where are x and y coming from? If I don't tell you, you have to kind of figure it out, but I might just simply just give it to you. I could say x is a WSU student, and then y is a food. I just tell you what it is. Now, you can make your life easier on problems by narrowing down your problem a little bit. You could simply say things like, okay, if we have this L of xy, and I want to talk about students in this class, it might make my life better to simply say, that's my domain. But if somebody says, no, you first have to talk about all students on the face of the planet and then somehow narrow it down to here. Well, then I'm going to need a whole lot more predicates to have that happen, right? If I did all humans, I would say, are they a student? And then, are they at Wichita State? And are they taking Math 321 at 8:30 in the morning? And those are all these features that a person must satisfy before we can talk about them. On the other hand, you could just simply say, let's just make that our domain. Ignore everybody else and only take you. So we can always get around a little bit by controlling the domain. The other one is what's called a natural domain. This shows up in things like calculus. Say f of x is equal to 1 over x squared minus 4. Is this a function? Well, in calculus, we normally say all real numbers. We want real numbers to real numbers in calculus, right? But there's two problems here. What happens if I plug in a 2 or a negative 2? I get a 0 in the denominator. I'm not allowed to have that, but I didn't restrict it. So normally what we do is say, yes, from real numbers to real numbers, this is not a function. Because functions say everybody, for example, everybody must be sitting. If somebody's standing, if I skip 2 students, I don't have a function. They must sit. So what would you do? You would say, okay, fine. It's a function if I ignore those 2 students standing up. Ignore you, this is a function. And that's what we do. A natural domain simply says things like, you focus on who is the natural input. And for us, it's all x, not 2 or negative 2, right? So if we do propositions, propositional functions, let's go back to L of, what's my square and triangle, denotes, getting close to, denotes the square loves to hit triangle. What do you believe the natural domains are? Like, for example, what should go into square? Well, you look at the predicate. What's the predicate? Loving to hit something, right? So what would be natural? A chair, would that be in it?
No, something sentient.
Right, they ought to have something that has emotion of something they can love, right, whatever you define that to be, and is capable of hitting. So what do you think is, what would you fit? We could say any animal, right? Have you ever had a puppy that loves to go around and like hit stuff just for fun, right? Or like you could focus, say, okay, what's a natural domain? We could say the universe of discourse for square is, say, all, let's just focus on us, people, right? But what would be the universe of discourse for triangle? What's happening to triangle?
Can be.
They're hittable. What do you think's natural? Is all what?
Physical things.
Physical things? Or how about this? Let's make it terrible. What? Puppies? No. Oh, let's go back. People. I don't know. Maybe that's not natural. Toys?
Pretty natural.
Maybe not toys. Balls, baseball, volleyball, whatever. But the question, it really, for a lot of these, if they don't tell you what it is, you kind of scratch your head and say, what should I pick that's natural? If you pick something rather non-natural, it really gets difficult to narrow it down. So a good choice of domain can make your life easier as you do these sorts of problems. All right. How do I take a propositional function and go into a proposition? The easiest one is evaluation. So if I had, for example, C of X denotes X loves to eat cheese. And in my universe of discourse of X is all people, right? So here's my, here it's going to be mapped to either true or false, and over here is all people, right? That's all people. C is doing this mapping, and in here is obviously Mark, because I'm a person, right? What's evaluation? Evaluation is just to simply say that, okay, what is C of Mark? It's like algebra evaluation. Wherever that variable was, I put the word Mark, and I simply have Mark loves to eat cheese. Actually, I love Swiss cheese, but anyway. And so for this one, it would be true, right? It's been evaluated, and so that's one way to do it. Just here's your universe of discourse. We'll start putting people in. Mark, John, Joe, you. Lactose intolerant, okay, not that cow cheese, maybe goat cheese, I don't know. So you're going through these particular things, and the answer is going to be either yes or no. But there's two more ways of evaluation. There's two more things I could do to this that are actually useful to me. There's things I can say about you. Let's take another example. Let's do H of something denotes the something hates math 321. I could pick a person, say Mark hates Math 321. John hates Math 321, right? That's evaluation. But I also could come in here and say, man, for some reason, all my students hate Math 321. I say, everyone in this room hates Math 321. All right, have I turned this function into a proposition? Is that statement for everyone in this room, everyone in my universe of discourse, they hate Math 321? That is either going to be true or false. So I can evaluate by saying all, everyone hates Math 321. What would be another way to basically, I didn't say one in particular, it wasn't an evaluation, I just simply said everybody in my set. On the other hand, I could come in here and be secretive and say someone in here hates Math 321. All right, that's also going to be either true or false. And those two techniques of saying all or some fall underneath what's called quantification. So 2 is for all x in domain P of x, or 3 is for some x in domain P of x.
What is that like for no x?
But no is the same thing as all. None is all. It's just saying that you're saying all is not. So they're the same thing. A none is an all. You're saying all is not. That's still an all. Some means some. Now, one of the things about some really means one or more. I don't know how many. I could have 1, 2, 3, 4, 5. I could have as few as one or as many as all. I just say some. Yes?
Are they not all direct equal a sum?
A not all is a sum is not. And we'll get that here in a bit. All right. Both of these together are called quantifications. The first one, since it's an all, is universal, everyone in the set. And the other one, the second one, since it's a sum, is existential. There exists someone who has this feature, and so that's called the existential quantifier of the universe of discourse. So, what we're talking about is, so the second one is universal quantification. Notation, it looks like this. Upside down A. Upside down A is the word for all. That just simply, that's all that says is for all x, P of x. And the third one is existential quantification. And for existential quantification, what would happen if I tried to turn the E upside down? It would still look like E. So what we'd rather do is instead of upside down, we go backwards. And that is for some. So the word for all is an upside down A. The word for some is a backwards E for existential. All right. One of the things that helps us on this is what we're doing is we have a universe of discourse. Here's my domain, the stuff I'm talking about, and there's a bunch of elements in here, right? The object, say H, is either going to go to true or false, right? Back to that whole hates Math 321. Evaluation goes here and just simply picks one in particular and asks, okay, where are you going to, say true or false? That is evaluation, right? On the other hand, universal says, does everyone, if I did evaluate them, all go to the same value? Right? All. So universal x, h of x, means all go to true. But what would be existential?
Your single evaluation.
At least one, right? I don't tell you which. One or more of the evaluations go to true. Would that make sense? Is everybody okay with that? So if we over here, we have all of our dots. We go over here on H. Over here we are true and we are false. And I don't know which. I would have maybe this one goes to true and maybe this one goes to true. Existential means one or more go to true. Is everybody okay with the arrow diagram version of this? Evaluation is, who do you go to?
Is existential one or more but not all? Or can it?
No, it includes all. Yep, that would mean that if it's true for all, it's true for existential. If everyone is sitting down, someone's sitting down. So if I came in this room and said, someone is sitting down right now, you're like, well, yeah, everybody is. Okay, that also gets down to a question of when would these not be true? When would it not be true if I came in here and said, everyone is sitting, what's necessary? Everybody has gone to true, right? Everyone here hates Math 321. When's that true? If everybody hates Math 321, when would it not be true? When there's at least one, right, that does not. And that one, that is usually called the counterexample. For example, is it true, is everyone in this room sitting? No, because I'm not. I would be the counterexample. Okay, when on the other hand is existential true? When there's at least one is sitting down. Okay, when would it be false? When nobody is sitting. Everybody please stand up. Okay, that gets down to that question of how do we handle the nots, right? When is this not true? When is this going to be true? The negation feature of how we handle negation is going to be based a little bit along the following. If the domain is finite, in other words, we have, say, x1, x2, x3, up to xn, right? There's a finite number of students in this room. So if I actually said, everyone in here hates Math 321, I could actually answer that question with a yes or a no by doing what? Going around the room and making sure everybody hated Math 321. If somebody said, I don't, then that's my counterexample. The statement would be false. Right? I could just handle it one at a time. If the domain is finite, then for all x, p of x is simply what? Check p of x1, check p of x2, check p of xn. Now, when will it be true? In only one condition, when all are true. What logical operator only returns a true if all of them are true? And. So this is and. So it ends up being that all is a bunch of ands. Why do I not have parentheses? Remember from what two laws allow me to drop the parentheses? Commutative and associative. So I don't need them. Okay, what about there exists an x, p of x? Well, I could walk around the room and ask the first person, and then ask the second person, and then ask the nth person, and we go through, okay? But when is this true? If I say someone in here hates Math 321, when's that going to be true? As long as one is. So if there's ever one truth, the entire thing becomes true. What logical operator has true as a denominator? Or. And so that's just a bunch of ors. Is everybody okay with that? So we just go through, and one thing you could do is short circuit, and sometimes this is actually a programming statement. If you have a bunch of ands, the moment you get a false, it's false, right? Now, do you ever notice that when you have a programming language, there's actually two ands? There's the short circuit and then continue on and. The short circuit and is, once you get a false, don't worry about the rest of the evaluations because it's false. Other ones are, you have to do the rest. Well, why would you want to continue to do the rest? Because in programming, there might be something more powerful than false, like a segfault. Let's say you're going through this and you're checking for not only when is this true or when is this false, you're also checking to say, is it allowed? Is this a good precondition? In other words, there might be something more important than false, which would be, oh, wait, there's a major flaw here. This thing's going to have a div by 0 at one point. This is going to, crash the program. I'm going to have a buffer overflow. Maybe you should sanitize all your input as well as check for falseness. And so that's why we have a short circuit or a non-short circuit. The same is true with the OR. Sure, if it's true, it's true. Should you skip? I don't know. Maybe you ought to check for something more important than that. On the other hand, this allows us to talk about negation. In case anybody was ever curious of why you have and, or, and or. All right, for negation, this would now make a whole lot of sense because we have a law. What would it mean for it not to be true that everyone in this room has a predicate? Well, that would be, if it's finite, it's not this. And what does De Morgan's law say? The not will distribute. But what would happen to all of the ands? They all turn into ors. And what's a bunch of ors? Existential. So a bunch of ands is a universal. A bunch of ors, all ors, is existential. And so it flips all of those. And this becomes logically the same as there exists something such that, and the not is on all the predicates, that you don't have the predicate. When is it not true that everyone, that there is someone who is not? That's the same thing. Well, what would happen if I would negate existential? It's not true that someone in this room is a person. What's that the same thing as saying? Everyone is not a person. Why? De Morgan's law. It's not true everyone is a person means someone is not a person. It's not true someone in this room is a person is saying for everybody they're not people. And it's just De Morgan's law. That's all that is. And so those are logically the same thing. Now, negation goes through, and so if you would have things, normally when we would do negation, so if you would have something like a little bit longer, what if it's not true that for all x there exists a y such that for all z that h, x, y, z. And so I have some sort of propositional function of three variables. Like x hates y but loves z. I don't know. That's your proposition. That's your predicate. If I would negate that, negation does exactly what you expect. The first all would become a what? There exists. The next exists would become a all. The next all becomes a there exists. And so you would simply say, okay, this would be logically the same as there exists an x such that for all y there exists a z such that it's not true that h, x, y, z. Does exactly like you would expect. Not all, it means there's some that are not. Not some means that all are not. And not all is some are not. And then we have the are not of the predicate. They are not the predicate. That's normally what we do with negation. We move it down until it negates the predicate, the thing that we're looking at. Like not blueness, not happy, not hate. All right. Some problems with how do we go from language into symbols and then back? Well, if you see a for all, if somebody says all, what are they really saying? universal quantifier. If they say some, they mean existential quantifier. What if they say some, if you have a word like all, then somehow we are going to have a universal quantifier of something. And it always, there's a variable that comes along. If you say some, there is going to be a existential quantifier of some sort. If I say none, that is a universal quantifier of not whatever the predicate is. So if they say none, what they really said was all or not. So those are some words that we start to parse out English, or we turn the symbols into English. We would say, okay, wait, you have an all or not? I'm going to say the word none. You see an all? I'm going to say all. All have this. Now there are some awkward things that are used at different times. Let's take some examples. What would a, for all x, let's use the book. They use C of x implies f of x, where this is comedian. This is funny. That's the predicate. Versus for all x, C of x and f of x. What does the first one say? If I put it in a long way, what would it say? For all things in my universe of discourse. Well, if I'm talking about comedians and funny, I'm going to talk about people, right? So for all people, implicate if they are a comedian, then they are funny. That's what that says. For all people, if they're a comedian, then they're funny. I can shorten that down to say, oh, wait a second. For all people, if, okay, I've grouped the comedians over here. If they're in the comedian group, they happen to be in the funny group, right? Now, the funny group could be larger than the comedian group because there's non-comedians that are actually funny, right? But it at least tells me that if I put them in, what would be another way of saying that? If you saw in my head, what I'm seeing is for all people, here's all people, if they're in the comedian group, they happen to be in the funny group. That's what that first one said. Another way of saying that is all comedians are funny. Would everybody okay with that? So I could shorten down that English sentence to simply be all comedians are funny. Now this is another feature. We tend to say things like this. All students are happy. All teachers are crazy. All people who love math are, I don't know what. Good at math, I don't know. Right? If I say things like that a lot, what would that automatically tell you about your symbol version? I'm going to use that. All smaller group are bigger group. So if you tell me all of one are the other, I'm going to put the first predicate and imply the second predicate. I would normally use it that way. What does the second one say? All people are comedians and are funny. So I just said the entire universe of discourse is only comedians and they happen to be funny at the same time. So this is just simply saying everyone is a funny comedian. Very different. So if I would say everyone that I ever could possibly imagine is these two things, I would use the second. Now, which one do you tend to say more often? All people are, or everyone is these two things? We tend to say all people are, but this now allows us to understand that if you say all people are, you're using the first symbols. If you say everyone has these two properties, I'm going to use the second. What do you think happens on existential? There exists an x such that c of x implies f of x versus there exists an x such that c of x and f of x. Existential means you got to find at least one. For all the people I'm considering, what does that first one say? For all people, I can find one, possibly, right, that if they're a comedian, then they're funny. Now here's a harder thing. You would say, there is a funny comedian. That seems to be what you would say. But this is not quite right. Would this be true if you found no comedians? If there are no comedians at all, what is implication going to be? False. Imply, I don't care. What's false imply anything?
False.
False implies anything is true. So if you found no comedians, that would be true, right? If there is someone that if they are a comedian, then they're funny, would be true if I didn't find any comedians. So we'd have to be a little careful. We normally want to say things like you would simply go through that. Okay, some comedian is funny. If you have any comedians. If you have any comedians, then fine. I normally want to narrow that down. But if you don't, I don't care. It's still true. A lot of people want to say some comedian is funny. So you have to kind of be careful. What does the second one say? There is someone in this group who is a funny comedian, which is actually what I wanted, which is there is a funny comedian. These are subtly different from each other. The second one says there is a funny comedian. The first one allows that if there are no comedians, it's still true. If there were comedians, it means the second. So normally, what are you talking about? Normally, do you allow, if I came in and said, there's a funny comedian, and then would you say I was lying if there weren't any comedians? Normally, I would say that you're lying, right? So that would mean that you would want the what? The second. If I allow for no comedians, I would want the what? The first, which normally we don't do. So really what happens is most of the time we're going to use this one and this one are the typical. But the other two do have their applications. They're just a little bit not said as much. All right, we'll do more quantifications tomorrow. All right, that's it. Oh, wait. We want to do attendance. I'm going to make you read ahead. This will be 1.5 and 3, C, and D. And we'll talk about 1.5 next class. Oh yeah, and hand your attendance out. I think we forgot that.